The objective of this topic is recognize graphs of common functions. So 7 functions that are frequently encountered in algebra are the constant function, the absolute value function, the standard quadratic function, the square root function, the standard cubic function, the identity function, and the cube root function. It's essential to know the characteristics of the graphs of these functions, so we're going to take a look at each one of these individually. So in the last group of lectures, we talked a lot about graphing lines. A line like this, for instance, could have the form y equals mx plus b. Or we had some other forms, y minus y1 equals m times x minus x1, ax plus by equals c. But all of these had one thing in common, and that is that the x was to the first power. And things where the x is just to the first power, we call linear, and linear functions graph as lines. I use the word function because a line in y equals mx plus b form or any other form is going to be a function. A function has no repeating x values. In other words, if this were on a larger graph, for whatever this x value is here, there will be no more than one point on the line that satisfies that. A line doesn't do this. It's a curve. It could be a graph of something, that's fine. But this wouldn't be a function. Because for, say, this x value here, there's that y value, and there's that y value, and there's that y value. That's where that vertical line test comes from. If you can draw a line and it hits in more than one spot, vertical line, that means there's an x value that has multiple different outputs. It wouldn't be a function. But as long as our line is y equals something and the something only has an x to the first power in it, then we can have positive slope things. I'm not going to draw slope guy again, don't worry. Negative slope things. Or even horizontal lines, because that would be y equals some number. These will always be functions. And that means instead of y equals, we can write f of x equals. It's like a special club, the function club. A vertical line would itself fail the vertical line test. But what's the equation for a vertical line? That's x equals something that doesn't involve y. So we can't solve it for y. So me saying it has to have y equals means that I'm right. Okay. Why am I reviewing all this stuff from the last chapter? Well, these types of lines are the first in the group of functions that we're going to examine today. We are going to learn about some basic functions, what their shape is, and we're going to memorize them. When I was in high school, my algebra teacher, Algebra 2, Mr. Martinko, Tink, he used to have these basic functions on the wall, on these posters that he drew up, and he would call them the poster kids. So today, we're going to learn the poster kids. Linear functions and the special case of the linear function, the constant function. Linear functions will have a standardized form, f of x equals mx plus b. Constant function, well, that's a slope of 0. That means the m is 0, which means that term goes away. So f of x equals b. So the constant function, that's a special case of the linear function. What's so special about it? If the slope is 0. Linear functions, graph as lines. We did all that stuff in the previous lecture group. One very specific linear function we're going to look at is going to be this. The identity function. The identity function when we see the word identity in math, it should make us think of another word, itself. The identity function is f of x equals x, or y equals x. It's the function where our input is x, and the output is itself, x, itself, the identity function. If we made an XY table, and I'm making a point of showing it's an XY table, but since we're talking about it as a function, x f of x means the exact same thing as xy. So don't think it's like more complicated. If we had some x values, -2, -1, 0, 1, 2, the y values, the output of the function, would be itself. In other words, if we had f of -1, Then we're plugging -1 in for x. When we plug -1 in for x, we get f of -1 is -1. The input of the function f when x is -1 gives us an output of -1. F of x is -1 when x is -1. Okay. We know how to plug things in at this point. That's the last group of lectures. The important thing for today about the identity function is going to be the graph of it. This is like y equals mx plus b if b was 0 and m was 1. Y equals 1x plus 0, y-intercept of 0, and a slope of 1. This is the same thing we would get if we were just plotting the points. 0, 0, 1, 1, 2, 2, -1, -1, -2, -2. So linear equations graph as lines. Let's talk about quadratic functions. These graph as parabolas. So these things. The parent function here is going to be f of x equals x squared. So y equals x squared. Our inputs get squared, and we'll get our outputs. Quadratic functions are squaring functions. The x is squared. So if I made a table for some points, f of x, and I want some negatives, 0, some positives, and I start plugging these in, finding f of -2 would be -2 squared, and -2 squared is +4. F of -1 would be -1 squared. -1 times -1, +1. F of 0 would be 0 squared. F of 1 would be 1 squared. F of 2 would be 2 squared. -2, +4. -1, +1. 0, 0. 1, 1. 2, 4. Parabola. Next, the cubic function. Don't worry, this is going to pick up. It's not all going to be fun drawing pictures today. The cubic function. I mean, it's going to be kind of fun drawing pictures. This is f of x equals x cubed. Let's see what this shape is by doing a table. X, f of x. I'll do some negatives, 0, and some positives. If I find f of -2 here, well, when we cube a negative, it stays negative. This is going to be -8. -1 cubed would be -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. -2, -8. -1, -1. 0, 0. 1, 1. +2, +8. So this shape is like a stretched parabola that's been taken in 2 different directions. It's this shape. We're just going to call it the cubic. It's cubic. Next up, it's going to be the square root function. F of x equals the square root of x. When I make my table this time, normally I put negatives, 0, positives. Here, negatives aren't going to do anything. They're literally not going to do anything because I can't take the square root of a negative number. Not in the real number system. And when we're graphing, that is the real number system. It's not complex. There's no such thing as I on the XY plane. So I'm going to skip the negatives and I'm just going to start with 0. I'm going to be creative about the things that I pick. I'm going to be smart. If I put 1, yeah, I can take the square root of 1. That's a good pick. But if I put 2 like I usually do, that's the square root of 2. That's not going to be nice to graph. What's the next thing I can take the square root of? 4. And then 9. If I wanted another point, I'd pick 16, and then 25, and then 36, and then 49. Because square roots of perfect squares, those are nice numbers. The square root of 0, f of 0 would be the square root of 0. That's 0. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. Now, you might be asking, what about the negatives? Well, normally, when we're solving an equation, if we had, say, x squared equals 9, and we took the square root of both sides, we would have plus or minus 3 as the answer. But here we're not solving, we're evaluating. We're taking a pre-existing radical x, and we're saying, hey, instead of x, all of a sudden, this is 9. What is this? And since we're explicitly being asked what is radical 9, and there's not a minus before it, that means we only use the positive answer. Now I'm going to show something related to that in a second, but I want to get these points up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And 1, 2, 3. That's enough there. So 0, 0, 1, 1, 2, 3, 4, 2, 5, 6, 7, 8, 9, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 3. There we go. So that looks kind of something like this. And it's because of my drawing that it kind of looks like a line, but it's not a line. It's making this shape. And it's starting at 0, 0. Let me make this a little clearer because I want that shape to be more visible. After all, we're playing with shapes. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. 0, 0, 1, 1, 2, 3, 4, 2. 9, 3. And it's going to keep getting shallower and shallower, not steeper. It's getting shallower. Does that look like anything? If I turned it on its side, you'd have half of a parabola. If I turn this on its side, you'd have the square root. There's the squaring function graphed on the same one. And it makes sense that these shapes are similar because one's squaring and one's square rooting. So as the squaring one gets steeper and steeper and steeper as you go, the square root one gets more and more shallow. So remember I said I'd come back and show you another one. This one is not a function. This one is going to be a full parabola on its side. And you can see why that would not be a function. Fails the vertical line test. This would be the relation x equals y squared. And there, our y squared. Y squared means not a function. This is different than this. And in order to make my point, I'm going to change the f of x back to y, because you might be going, yeah, one has y, one has f of x. Of course they're different. No. These are different too. Because here, it's explicitly the positive radical. The square root sign is already there. Here, the square root sign is not there already. So when we solve it for y and take the square root of both sides, we have to remember to take the plus or minus. And it's that negative square root that fills in the bottom. So far, our functions, we've got our lines, we've got our parabolas, we've got our cubics, we've got our square roots. Next up is going to be the cube root. The cube root function is going to be f of x equals the cube root of x. So I'm going to use smart x picking again. I can take cube roots of negatives. We used perfect squares for x's. For the square root function, let's use perfect cubes. -8, -1, 0, 1, and 8. The cube root of -8 is -2. The cube root of -1 is -1. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is 2. So let's see how we get this shape I promised you. I need 1, 2, 3, 4, 5, 6, 7, 8 that way. 8 that way. I need 2 up, and I need 2 down. -8, -2. -1, -1. 0, 0. 1, 1. 8, 2. And that's the graph. The absolute value function. It's going to be f of x equals, you guessed it, the absolute value of x. Table. I'll pick some negatives. 0. Some positives. It's a function, so instead of y, we'll call it f of x. The absolute value of -2 is +2. The absolute value of -1 is +1. The absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. If I plot these three, 0, 0, 1, 1, 2, 2, that part of it looks very much like the identity function. Is this the reference? No, it's not. But these, the negative x's, are also giving positive y values. So instead of it being continuing on like the identity function, it goes that way instead. So the absolute value function has this equation and this shape. The objectives of this topic are use vertical shifts to graph functions, use horizontal shifts to graph functions, use reflections to graph functions, use vertical stretching and shrinking to graph functions, use horizontal stretching and shrinking to graph functions, and graph functions involving a sequence of transformations. So let's start off by talking about vertical shifts. Vertical meaning up or down, shifts meaning picking up the graph and moving it up or down. Let f be a function and c a positive real number. Then the graph of f of x plus c is the graph of y equals f of x shifted c units vertically upward. And the graph of y equals f of x minus c is the graph of y equals f of x shifted c units vertically downward. So add a real number to a function, we move it up. Subtract a real number from a function, we move it down. And the number we add or subtract is the same number of units that we move up or down. Let's say we had the function g of x equals the absolute value of x minus 3. And we wanted to graph this. Well, we would ask, what is the parent function? And the parent function, since we have an absolute value in here, would be the absolute value of x. Okay. Parent function's the absolute value of x. We know what that looks like. That looks like that. So when I'm saying you need to know those shapes, you need to know that something that has a function that looks like that has a graph that looks like that. When we see a function that has an absolute value in it, we know the absolute value parent function is the absolute value and that it looks like this. See this down 3, this minus 3. Taking that and subtracting 3 is going to move it 1, 2, 3 down. And that's how you move graphs up and down. Let's look at another. Let's say we had h of x equals x squared plus 2. Ask yourself, what's the parent graph? Well, this is a squared So the parent graph is f of x equals x squared. What's happening to the x squared? We're adding 2. Well, what does that mean? It means the original x squared graph looks like that. If we move it up 2, it'll look like that. How do we know where to draw? Well, the original had 0, 0. That'll be our new starting point, and everything gets moved up 2. So if we went right 1 up 1 to get to 1, 1, here we would go right 1 up 1 to get to that next point, and we draw our parabola through it. Horizontal shifts. Let f be a function and c a positive real number. Then f of x plus c is a left shift. F of x minus c is a right shift. So this is actually the opposite of what you'd expect most likely, because plus c makes you think positive, makes you think go to the right. Minus c makes you think negative, makes you think go to the left. But for left and right, it's the opposite of that. Plus c is actually to the left. Minus c is actually to the right. And these pluses or minuses are inside the parentheses with the x, not added or subtracted to the whole function. Let's take a look at a g of x equals x plus 1 squared. Well, this is a squaring function. It's quadratic. We've got a square on it. So that means the parent function is f of x equals x squared. And we know what that looks like. That looks like this. Plus 1, when it's added to the x and not to the square, not to the whole function. Plus 1, that's going to move to the left one. So it's our normal quadratic moved left 1. What if we want to do both at the same time? We can do that. Let's say we have p of x equals the square root of x minus 3, where the x minus 3 is under the radical, and then minus 2, where the minus 2 is outside of the radical. Well, the parent function, f of x, that's going to be the square root of x. And we know what that looks like. The square root of x looks like this. This minus 2 on the outside, that's telling us to go down 2. This minus 3 on the inside that's just subtracted from the x, that's telling us to go right 3. So from the starting point, we go down 2, we go right 1, 2, 3, and there's our new starting point. Then up 1 over 1, you know, and then all the same countovers as the parent graph. It's like we take the parent graph and we subtract 3 minus 3. We move it to the right 3 and we move it down 2. So this point, whatever it is, we would move it right 3, down 2. So maybe I should have been up here somewhere. But anyway, I'm just drawing shapes. Could we do one more of these? Yes, absolutely. Q of x equals the square root of x plus 2 with the plus 2 with the x, and then on the outside, minus 5. Watch this. We know the shape of the square root. It's the that thing. So instead of it 0, 0, that minus 5 on the outside is down 5. That plus 2 with the x, it's the opposite of what I want. So that's going to be left. So if I go down 5 from the normal starting point and left 2, there's my new starting point. That's my new second point. So it's something like that. Assuming that this is just up, down, left, right movements, what would this be? Assuming it's just up, down, left, right. Well, it's an absolute value. 1, 2, 3. It's moved up 3. And it's been moved 1, 2, 3, 4 to the right. And I'll give it a name. Call it C. That's all you do. I'm going to come do that thing I wanted to show you now. I want to take a look at h of x equals x plus 3. If this was y equals mx plus b, then m, the slope would be 1, and the y-intercept would be 3. 1, 2, 3. And then we'd go up 1, over 1. Or down 1, left 1. So my question to you is this an upwards shift of the identity function? F of x equals x? Because we're adding 3 to the whole thing, so it should be up 3. But wait a minute. This can be considered just adding 3 to the x. So is it left 3? Is it up 3 or left 3? Well, you can see if I put the identity function in, it doesn't matter. It is both 1, 2, left 3 and 1, 2, up 3. The identity function, since all it is an x, since there's no symbol around the x, up movement is the same as left movement. And that's what makes this special enough to give it its own category separate from just a regular linear equation. Okay? So with the identity function, a plus 3 here, that can be considered up 3 or left 3. So now we know how to move up, down, left, right. Let's talk about reflecting. First, we'll talk about reflecting about the x-axis. The graph of y equals negative f of x is the graph of y equals f of x reflected about the x-axis. So to use the x-axis as a mirror, we take the opposite of the function. To reflect about the y-axis, to use the y-axis as a mirror, we take the opposite of the x inside of the function. So an x-axis reflection, a vertical flip, that's negative f of x. A horizontal flip or a reflection about the y-axis, that's f of negative x. Use the graph of f of x equals cube root of x to obtain the graph of h of x equals cube root of negative x. Well, here the negative is inside the radical with the x. That's f of negative x. That's a flip horizontally, a reflection about the y-axis. So we take our original graph shape, and anything to the right moves to the left, anything on the left moves to the right. So we get this red h of x, cube root of negative x. Notice this actually would have been the same as negative cube root of x. The reflection across the x-axis would have given us the same red graph. And that's because the cube root of a negative number is negative. It is the same to say negative cube root of x is the cube root of negative x. Just something interesting happening in this example. But that means if you chose the wrong reflection, you accidentally got it right. If you reflected across the x-axis, you accidentally got it right. A vertical flip and a horizontal flip. Now, when I'm talking about a vertical flip and a horizontal flip, imagine we had our graph. A vertical flip would hold the x-axis still and spin it. So just like a pinwheel. The stuff from the bottom ends up on the top. The stuff from the top ends up on the bottom. In other words, we change our y value to its opposite. Negative y's move up to positive. Positive y's move down to negative. So a vertical flip is when we take don't write down what I just wrote. It's the opposite of what the correct answer is. A vertical flip, we're going to take the y values and make them their opposites. So whatever we have for the function, the output, we take the opposite. It's a negative outside of the function. A horizontal flip would treat the y-axis as the thing that doesn't move, and the pinwheel effect would happen. The pinwheel effect would happen left to right, horizontally, flipping things that are on the left to the right, flipping things that are on the right to the left. So we're taking our x value and taking its opposite. A horizontal flip is taking the opposite of the x. So just like vertical stretching and vertical shrinking is referred to as horizontal shrinking and horizontal stretching, depending on whether we are multiplying by the whole function or just multiplying by the x. Vertical things are up, down, adding, subtracting, multiplying by the whole function. Horizontal things are left, right, adding, subtracting, multiplying by just the x. Same here. Vertical flip, where the x-axis is the point of revolution. Since it's flipping everything vertically, that's up, down. That is the opposite of the whole function, a negative with the whole function. Horizontal, left, right. That's taking the opposite of just the x itself. Horizontal is x stuff, vertical, y stuff. So if we had, I'm just going to draw 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. That's all we're going to need on left and right. Okay, so from -3 to +3, I have points on the y at +3, +3, +1, +2, 0, -1, +1. So that's each of those 7 points: -3, -2, -1, 0, 1, 2, 3. It's at +3, +3, +1, +2, 0, -1, +1. This is f of x. I would like us to draw negative f of x. And actually, I'll bust out another color here. Negative f of x is going to be in green. So we're going to take the opposite of the f of x, the opposite of the y value. Instead of 3, it'll be at -3. Instead of 3, it'll be at -3. Instead of 1, it'll be at -1. Instead of 2, it'll be at -2. Instead of 0, it'll be at 0. Instead of -1, it'll be at +1. Instead of +1, it'll be at -1. I literally just took the opposite of each of my y's, each of my f of x's, and made that the new point. And now, what do I have? So it's not wanting to be very agreeable in terms of seeing everything. There we go. It's a vertical flip. I'm not going to do it, but if I swapped all the x's for the x, you know what? I'm going to do it. I'm going to do it in red. I'm going to attempt to make the red show. There was a reason I was just using black and blue today. F of x, sorry, red's going to be f of, you know what? I have enough colors left that I could use black. In black, f of -x. This should be a horizontal flip. We're going to take every x value and replace it with its opposite. So I'm doing it from the blue. Instead of an x of -3, this one would go to an x of +3. So the y is staying the same. Instead of this being at -2, it's going to be at +2. But the x is changing. Here, the y stays the same, but instead of -1, it's +1. Here, the y stays the same, but for x, instead of 0, it's 0. So that's our point of revolution. Here, instead of 1, it's at -1. Here, instead of 2, it's at -2. I'm glad I did it. This is hard this way. Here, instead of 1, or sorry, instead of 3, it's at -3. It's the blue one revolved around the x-axis. So again, vertical flip, the opposite of the whole function. You take your opposite of your y's. Here, horizontal flip, you take the opposite of your x's. vertically stretching and shrinking graphs. Let f be a function and c a positive real number. If c is greater than 1, the graph of y equals c times f of x is the graph of f of x vertically stretched by multiplying each of its y coordinates by c. But if c is between 0 and 1, if c is a fraction between 0 and 1, the graph of y equals c times f of x is the graph of f of x vertically shrunk by multiplying each of its y coordinates by c. So let's use the graph of f of x equals absolute value of x to obtain the graph of f of x equals 2 times the absolute value of x. 2 is greater than 1. Therefore, this is a vertical stretch. Every function output for each value of x is going to be multiplied by 2. So for instance, 1, 1 on the original graph becomes 1, 2 on the new graph. 2, 2 on the old graph becomes 4, 2 on the new graph. Sorry, it becomes 2, 4. All of our y coordinates are multiplied by 2, giving us that stretching effect. So far we've seen that things happening to the function happen vertically. Things happening to the x happen horizontally. So horizontally stretching and shrinking a graph, instead of looking at c times f of x, we're looking at f of c times x. The c is multiplied by the x instead of by the function. If c is greater than 1, then it's a horizontal shrink. If c is a fraction between 0 and 1, it's a horizontal stretch. A horizontal stretch is a vertical shrink. A horizontal shrink is a vertical stretch. Think about it. If you pull something vertically, it's shrinking horizontally, like a rubber band. If you pull something horizontally, it shrinks vertically, like a rubber band. So use the graph of f of x equals x squared to obtain the graph of g of x equals 1/2 x squared. This is going to be a horizontal stretch. Start with our original function and stretch it horizontally. Now every x that we would plug in gets cut in half before we square it. In other words, it takes twice as much x to get just as far. But a horizontal stretch is a vertical shrink. So you just have to remember, fractions shrink vertically, so they would stretch horizontally. Just like a rubber band. this one, the opposite of the square root of the opposite of x plus 2. What order do we do things in if we wanted to graph this? Obviously, we're starting with f of x equals the square root of x. So our starting position is the square root of x graph. It does turn out that just like we have an order of operations, we have an order of transformations. And if we don't follow it, we don't get the right final graph. And we're going to talk about the order of transformations. First, we're always going to take care of our horizontal shift. That's our left-right movements. Second, any horizontal or vertical stretch or shrink. First, horizontal shift. Second, horizontal or vertical stretch or shrink. Third, our reflections. And those would be across the x-axis or across the y-axis. Over the axes, AXES is the plural of axis, AXIS. And then finally, the vertical shift. Our up, down. So the order of transformations, which you probably didn't even realize was a thing, I, being the teacher, totally knew it was a thing. You'll never know. I did. The order of transformations. Horizontal shift, left, right. Our horizontal or vertical stretching or shrinking. Remember, a horizontal stretch is a vertical shrink. A vertical stretch is a horizontal shrink. So that's why it's all in the same step. They're really the same thing. Third, our reflections. Flip over the x-axis, flip over the y-axis, do both, whatever it's telling you to do. And then finally, the moving up, down. So here, negative square root of the opposite of x plus 2. What our first transformation should be would be the horizontal shift. And here, that's whatever we're adding or subtracting to the x. Plus 2 with the x, remember, is the opposite of what you'd think it is. Plus on a number line with the x would normally mean right. I'm going to my right, but you're seeing me go to your left, so this is confusing. Let me not do anything with the camera. Let me just use my hands and keep them below, because as we figured out before, if I move my hands to the right on the board, they go to the left up here. So I'm going to keep them below. Here we go. Normally, when we add or subtract to the x, we can think of it as being the opposite of what we would normally want to do. Adding 2 to a number line normally moves us right. But when we see +2, it's actually going to be shifting the whole graph to the left. That's right. The graph, like everything you own in that box, is going to the left. And that is one plus of remembering that song. I don't know. I'm just throwing things to the wall, hoping they stick. Anyway, we're going to move it left 2. 1, 2, boom. Now it looks like this. So we've taken care of our horizontal shift. We move on to any horizontal or vertical stretching or shrinking. We can get that by multiplying y values by numbers or fractions, multiplying multiplying x values by numbers or fractions. But here we don't have any stretches or shrinks. So I can just go ahead and knock that out too. Reflections across x and y axes. And here we have both. Here is a reflection. And there's a reflection. The one on the outside is the one that flips it over the x-axis. That one is our vertical flip. And then this one on the inside, that is our horizontal flip, our flip across the y-axis. So all of the points from over here move over here. Since we were 2 to the left, we would be 2 to the right. So our reflections, they're done. And then vertical shift, we don't have anything on the outside added or subtracted. So that one's done too. So our final graph would be the square root 2 to the right. And instead of going up and right, it ends up down and left. How did we get there? Well, we followed our order of transformations. First, our horizontal shift +2 took us 2 to the left, Then we flipped over the X and we flipped over the Y. And those were all the transformations we had. We end up with this graph.